For this lab, we used the Cal Poly low-speed wind tunnel to analyze different types of flow over a cylinder. We determined the pressure drag coefficient using discrete pressure measurements taken on the surface of the cylinder and evaluated the effect of changing the Reynolds number as well as the surface roughness. The goal was to see if we could reduce drag by adding strips of sandpaper at the point of flow separation to trip the flow into turbulence and stay attached longer. In order to visualize the flow, a fog machine was placed at the front of the wind tunnel, and a floodlight and laser located on top of the wind tunnel were pointed downwards onto the stream.
Our group made a few assumptions, such as the cylinder diameter being 0.1588 meters, which is a conversion of 6 1/4 inches to meters. We also assumed that the density of air during these tests was 1.225 kilograms per cubic meter. We also assumed that 150 RPM corresponded with 5 meters per second, 350 RPM with 14, and 700 RPM with 30. We also took the kinematic viscosity of air to be 1.85 times 10 to the negative fifth Pascal seconds for our Reynolds numbers calculations. To organize our experimental data, our group decided to generate two plots, one for drag and one for coefficient of pressure for each trial run. The pressure measurements taken at the wind tunnel are measured as a difference between the pitot tube at the front of the wind tunnel and the pressure measurement at each port around the cylinder. So this had to be converted to total pressure. In order to change this pressure measurement into a force, we had to multiply the pressure reading by the surface area corresponding to each port, which is its arc length around the circular cross-section. The x components of these force vectors were then summed to find the total drag on the cylinder. For the coefficient of pressure plots, the ideal curve was found using the analytical solution to find that the coefficient of pressure is equal to 1 minus 4 times the sine squared of theta. The measured coefficient of pressure was calculated using the difference between the measured pressure and free stream pressure at each port around the cylinder. The orientation of this graph is such that 0 is directly facing the flow, 180 degrees is at the trailing edge of the cylinder, and then 360 degrees is back at the leading edge of the cylinder. Before calculating the coefficient of drag, our group had to decide on an area convention to use. We didn't want to use the typical aircraft convention of area seen from above because a cylinder is not quite a thin airfoil. Frontal area likewise did not seem to capture the geometry of the circle. So in light of this, we decided to use the circular cross-sectional area. So although this is not exactly what the flow sees, we figured that because we're analyzing more of a 2D flow, this would be okay. Also, ultimately, we're comparing the different trial runs on the same geometry, so it will kind of just scale with the drag force and the velocity of the flow. In order to calculate Reynolds number, our group used the equation that you can see on screen. And using these assumptions for the density of air, the velocities at 150, 350, and 700 RPM respectively, the diameter of the cylinder, and the mu value for air at STP, we calculated these Reynolds number values. And in order to calculate the Strouhal number, using the equation that you can see on screen, frequency was counted in the video by watching in slow motion, so our results may be skewed due to that. And using the same length and velocity numbers, we were able to calculate these Strouhal numbers.
Capturing the flow at 5 meters per second provided the most visible flow patterns. However, the Reynolds number is too low for the pressure readings to provide any meaningful data. At 14 meters per second, it can be clearly seen that the trip tape creates turbulent flow within the boundary layer, and the flow becomes more attached to the cylinder. Increasing the velocity to 30 meters per second caused the most attached flow out of all three velocities when the trip tape was being used.
Before analysis of the coefficient of pressure charts takes place, the spike at the 235-degree port must be addressed. We believe this spike to be due to an incorrectly calibrated pressure sensor that would often output values inconsistent with the rest of the data we had collected. We believe this to be a calibration issue due to the fact that this offset seems fairly consistent throughout the entire experiment, as shown by the lessening of the magnitude of the peaks compared to the rest of the data, as the RPM of the wind tunnel fan increased.
Comparing the coefficient of pressure plots, we have circled the points at which the flows appear to separate from the cylinder because they seem to greatly deviate from the ideal inviscid plot. A dotted line was used to reinforce this idea as it represents the region in which the pressure coefficient remains constant over a large angular portion of the cylinder, indicating the pressure is not changing as a function of angular displacement around the cylinder because the flow is no longer attached. In comparing the runs at 5 meters per second, you can see the plots of tripped and untripped seemed fairly similar, although the cylinder with the trip strip seemed to be slightly less ideal than the cylinder without the trip strip. This phenomenon reverses as we move on to the plots comparing the flows at 14 meters per second, in which you can see the tripped flow seems to stay attached for approximately 15 degrees more around the cylinder. Both pressure coefficients seem to level off at the same place around the back end of the cylinder between the region of 135 and 225 degrees, possibly indicating that no matter what we try, the flow will always separate there. The flow around the cylinder at 30 meters per second seems to be the most ideal out of all the trial runs. It dips along with the ideal pressure coefficient plot, indicating it is staying attached over the top of the cylinder where the coefficient of pressure would be the lowest, although it seems to separate where the flow is separating at 14 meters per second, just like the untripped flow seems to be about the same as that of the untripped flow at 14 meters per second. When comparing the tripped versus untripped trial runs, you'll notice first for the 5 meters per second case, the drag and coefficient of drag was less for the untripped cylinder, but then once we move up to 350 RPM or 14 meters per second, this reverses, and now the cylinder that had the trip strip on it records a lower drag force and coefficient of pressure. And this continues when we look at the 700 RPM case, in which you notice that the drag and coefficient of drag on the tripped cylinder is much less than that of the untripped cylinder. Interestingly enough, the highest coefficient of drag was actually found for the tripped cylinder, the cylinder with the trip strip, on the 5 meters per second run. Interpreting our results, our group noticed a few things. The first was that these coefficient of drag numbers seemed very high when compared to those typically given for shapes such as airfoils. Now this must be one of the reasons why cylinders are not favorable aerodynamic shapes. Our coefficient of drag numbers could also be high though because of our convention of using cross-sectional area, whereas typically for shapes such as airfoils, they use the area that you would see from above when you have a full wing. Another thing we notice is that the trip strip seemed to be most beneficial at higher flow velocities. If you remember at the slow flow of 5 meters per second, the cylinder with the trip strip had a higher drag and coefficient of drag than that without the trip strip, whereas once you moved on to the 14 and 30 meters per second flow, the trip strip seemed to be very beneficial in making the coefficient of pressure versus theta plot be more ideal than that without. We also noticed that the drag plot, exterior force vectors all look very similar. Now, this is probably because we converted the pressure measurements given from the wind tunnel, which are differences between the port measurements and the tube at the front of the wind tunnel, and converted them to total pressure. In this case, they're all on the order of about 100,000 pascals, so a variation in just a couple hundred or even 1,000 of these is only going to be about a 1% difference. So when we plot these pressure or force vectors around the cylinder, they all only vary by about 1% length. Therefore, they all look about the same.
There were 4 main sources of error. First, the trip strip detaching from the surface of the cylinder meant a portion of the boundary layer staying laminar and detaching earlier than it should have. Second, the cylinder being only partially affixed to the test section walls left room for vibrations when gathering data, especially at 700 RPM. Third, having the cylinder out of true with the axis normal to the airflow means that our calculations assuming 2D trigonometry are off. Lastly, the poor quality of the flow visualization video did not allow for accurate calculation of the frequency for the Strohal numbers.